In module 1, we have gone through some basic concepts and results in the context of simple random sampling with and without replacement. But as I said, there are a lot of things to come. We have to have a very clear understanding about the behavior of y bar star. That is something that you are not supposed to know at the undergraduate level. So, we will take up that particularly in our module 2. In the context of with and without replacement sampling, as I said, we have some more things to take up, but for the time being, to start with, if you have any question, then you can raise your issues to me and then we can start discussion from your questions that are coming up in your mind.
Sir, I think now we should address two related questions. Expression for the expectation of 1 over nu and estimation of capital S squared. Also, now that we have explicit expressions for the variances of y bar and y bar star, we should have a concrete proof of the claim that variance of y bar is more than the variance of y bar star.
That's right. We will take up one by one. Fortunately, these topics have been thoroughly discussed and documented in the literature. As to your question 1, it turns out that expected 1 over nu, it was shown in the context of module 1, expected 1 over nu is nothing but 1 to the power n minus 1 plus 2 to the power n minus 1 all the way n to the power n minus 1 divided by n to the power n. So, the last term is of course 1 over capital N and plus etc. etc. As to your question number 2 regarding unbiased estimation of the population variance S square, we have a number of alternative solutions, and also your question refers to the variance of y bar greater than variance of y bar star. So, D. Basu was the first to hint on the result of supremacy of y bar star as against y bar in terms of the estimation of the population mean capital Y bar by using y bar star as against y bar. But his result invoked sufficiency principle in finite population sampling, and I find it a bit difficult to explain at this stage. On the other hand, by now we have good analytical proofs available. More of it will follow. Based on the entire data under with replacement sampling including repeats, we can have usual estimate of sigma square, and hence we can obtain one for S square via the relation between the two. Remember, under with replacement sampling, all the observations are sort of technically what we call IID. So, because they are IID observations, the sample variance with a divisor little n is an unbiased estimate of the population variance sigma square. And we know the relation between sigma square and S square, namely capital N sigma square equal to capital N minus 1 S square. From that connection, we can get an estimate of S square. On the other hand, the moment we look at the structure of with replacement sample, we know that we can bring in the concept of dividing the sample space into different aspects corresponding to the values of nu, the number of distinct units, the concept of C sub nu, all the collection of samples having new distinct units and its cardinality, and the structure of the samples inside this subspace, and from there we can, and recognizing that they refer to without replacement sampling, we can straight away apply the results of without replacement sampling and claim that S square nu, which is summation over all units, distinct units in the sample yi minus y bar star nu whole square divided by nu minus 1, this is an unbiased estimate of capital S square. All we are doing is we are putting good old result from simple random sampling without replacement, which says that the sample mean based on all these units with a divisor n minus 1 or nu minus 1 in this case is an unbiased estimate of capital S square. The only point to be noted is the possibility of nu equal to 1. In that case, this structure S square nu is ruled out. That is the only possibility that we should remember, and we should do something about it. So, what is our solution in this particular case?
Sir, I think I can figure this out. What about s squared hat equals 0 in the case nu equals 1, and equals s nu squared divided by 1 minus n raised to the power of 1 minus small n for nu more than 1. In that case, direct computation yields this. Expectation s squared hat is etc. etc.
Ultimately, it is coming to s squared.
S squared.
Okay. Yeah, very good. So what you are doing, because for mu equal to 1 you cannot do anything, you set s squared estimate equal to 0 for mu equal to 1. And for all other cases, all you need to know is you are talking about a truncated distribution. So you look to the probability of mu equal to 1, p nu equal to 1, you take 1 minus that and divide by that. That's exactly what you are doing. S squared nu divided by 1 minus probability nu equal to 1. And that will make for every nu greater than 1, because s squared nu conditional on mu is unbiased estimate for capital S squared. This will give you s squared multiplied by summation probability mu greater than 1, and that exactly same thing in the denominator, so that will cancel out and you will get s squared. Very good. It's a very simple interpretation of the thing and a very simple correction that you make. You are just right. Now regarding your last point, we need to show that variance of little y bar, which is sigma square by n, under with replacement sampling, variance of little y bar, that is more than variance of little y bar star, which is capital S square multiplied by expected 1 over nu minus 1 over capital N. We must remember the proof of the right hand side of this inequality, that refers to variance of y bar star. To compute that, we are looking at variance of y bar star for given mu. The moment you say you are restricting to the subclass of samples where mu is fixed, that subclass is behaving like without replacement sample of size nu, and hence the variance is s square 1 over nu minus 1 over capital N by referring to without replacement sampling. And then all that you need to do now is taking expectation. But mu is the only random variable in the whole context, and you are talking about expected value of 1 over nu. That's why that expression comes. Now you need an analytical proof of this result, sigma square by little n greater than s square times something. But then you know the connection between sigma square and s square. Multiply both sides by capital N, for example. In the left hand side, capital N sigma square you can replace by capital N minus 1 s square. That is how s square will cancel out from both, and it amounts to the expression shown here. The last line says 1 over little n minus 1 over little n capital N, that should be greater than expected 1 over mu minus 1 over capital N. So this is the inequality that needs to be established in order that you can show that y bar has a larger variance than y bar star. This inequality is a bit tricky. We need a detailed expression for expected 1 by nu. I have given you the result over there in the previous one, and that still once you have the result, exact expression for expected 1 by nu, you need to establish this inequality. So there are interesting articles on this inequality particularly. I recall long time back, Professor M.C. Chakraborty of Bombay University, they introduced this Journal of Indian Statistical Association, GISA, and in the first volume, which came out in 1963, Professor Chakraborty has a very interesting article precisely on this topic, and he gave a novel proof of this inequality that is laid down over here. So that paper is definitely worth reading. I can also mention about a paper by Color and Shortling on getting a derivation for the expected value of 1 over nu. For small n equal to 2, one can see that the two expressions are identical. And it would be good to think for a moment, why is it so that there is no difference between y bar and y bar star if small n equal to 2? If small n equal to 2, there are two possibilities. Either two units are equal or the two units are distinct. If they are equal, then it makes no difference between y bar and y bar star, because you are referring to the same unit. And if they are different, then also y bar and y bar star, they become the same. Therefore, for small n equal to 2, for every sample, computation of y bar and computation of y bar star makes no difference. Therefore, the two are identical. But for n equal to 3, one can work out expected 1 by nu and put in that inequality, and one can show for himself directly show that yes, that inequality is valid. But this is only for small n equal to 3 or 4 and for capital N equal to etc. etc. We need a general result. In this context, I am tempted to mention about one interesting article by Professor P. K. Sen and myself. That paper came out in Shankha, the Indian Journal of Statistics, from ISI in 1989. There we have developed a very nice group theoretic argument to establish the superiority of y bar star as against y bar. We also discussed many other related results and gave expressions for the general expressions for the expectation of negative powers of nu. Here we are talking about expected 1 over nu, that means nu to the power minus 1. We gave general expression for expectation of nu to the power minus 2, minus 3, etc. And there are many other things that we had developed. That's an interesting paper. It is worth reading. That paper is, this is the details on averaging over distinct units in sampling with replacement, that is by myself and Professor P. K. Sen, that appeared in 1989, Shankha Series B. Okay, to sum up, there are a lot of issues, interesting issues that come up under simple random sampling with and without replacement, particularly for with replacement, the issue of the number of distinct units, the issue of estimation of the population parameters like mean and variance, and more than that, establishing the superiority of the mean of distinct units as against the mean of all units including repeats. And this is only about the mean, and if I am talking about the estimation of variance, whether I should use the mean based on all units or I should use the mean based on distinct units, and then working out, showing the unbiasedness of the two estimators is okay, but then going further, one step further, computing their variances of the estimates, and then comparing them, that is going to be a very difficult task. So there are a lot of issues still there. Now we will see what is in store for us for the questions and MCQs. Yeah, this part was a bit small section. I did not want to overburden you with a lot of new ideas, but the point that we wanted to make is, in respect of simple random sampling with replacement, that is a non-trivial issue of working out the parameter estimates based on distinct units in the sample, trying to understand the nature of the samples so derived, nature of the estimators so found out, and their overall performance in respect of the whole lot of samples. And these are non-trivial issues. We will show that some of the results are really a bit tricky, definitely not at undergraduate level, something is even at research level. Expression for expected value of 1 over nu, I did not give the derivation of the result, nor I told you how to prove the variance inequality, which eventually boiled down to an algebraic inequality in terms of small n, capital N, and the expected value of 1 over nu. That is also a function of small n and capital N. So, all these things are kind of non-trivial issues, and I ended up referring to the paper by M.C. Chakraborty in Journal of Indian Statistical Association 1963 volume 1, and also a more recent paper by Sen and Sinha, myself with Professor P. K. Sen, that appeared in Shankha in 1989. Our paper is worth reading, that has many issues discussed. So, we will stop now and we will look forward to the exercises and MCQs. Okay, let me give a small introduction before we get into the questions. In our times, I am talking about almost 50 years back, when I was an undergraduate student. In our time, in this undergraduate course in survey sampling, it started with random number drawing, etc. Then immediately landed into simple random sampling with and without replacement, and whatever you are taught, they seem to be pretty simple. Results under with replacement, results under without replacement. At one point of time, we thought with replacement is easier than without replacement. Then we thought, yeah, both are okay. But the point is that we missed talking anything about the mean based on distinct units, the notion of distinct units and its relevance in the study of sampling procedures. So that part was missing. That is why they looked okay. But now you can see there are a lot of issues involving with replacement sampling, particularly the issue of distinct units. So all the questions here they are referring to with replacement sampling, and let's see how the questions are coming up. Okay, please start.
Question 1. Under simple random sampling with replacement, capital N, small n, verify that the expectation of mu is equal to n times 1 minus capital N minus 1 divided by capital N raised to the small nth power.
Okay, so this question is very tricky. When we are talking about nu, we know that nu is a random variable and it has a distribution. It assumes values 1, 2, 3, etc. technically up to the smaller of small n and capital N. And then we know the distribution of nu, that is why we are referring to Wheeler's book, the problem on classical occupancy, and the expression for probability nu equal to k, that is n choose k delta k o n divided by capital N to the power small n, etc. So from that we can use the first principle, apply the definition of expectation and work out expected mu. That would be a good training for you. You know the distribution of mu, work out from the first principle expected value of mu. There is another tricky way of doing it, that is what one should try to venture into. Can I express mu as the sum of the indicator functions of the units in the population? So nu is nothing but, if I define indicator function capital I suffix small I as equal to 1 if the unit I is included in the sample, equal to 0 otherwise, for every little I equal to 1 to up to capital N, then this nu is nothing but sum of the indicator functions of all the units in the population. And from there we can show expected mu is nothing but expected value of sum of indicator functions and expected value of a sum equal to sum of the expectation. From there you can, in one line, you can get this expression. You can see how simple it is to view, to derive this result by viewing mu as the sum of appropriately defined indicator functions. And from there also you can work out the variance of the distribution of mu. Next question, please.
Under simple random sampling with replacement, capital N, small n, verify the formula for the expectation of 1 over mu for a general capital N when small n is 4.
Well, this is basically a question involving algebra. You know the expression for expected 1 by nu, the general expression, and then you are supposed to verify this when small n equal to 4. The idea is that when small n equal to 4, you can explicitly see for yourself the distribution of nu equal to 1 or 2 or 3 or 4. You can write down the distribution directly, you can work out expected mu, and then you can verify the formula that is given. The formula is tremendously simple. It says 1 to the power n minus 1, 2 to the power n minus 1, etc. In this case, because n equal to 4, the result is 1 cube plus 2 cube all the way up to capital N cube divided by capital N to the power 4. And you know that you can simplify this thing immediately. So you are supposed to verify this result. Next one.
Under simple random sampling with replacement, capital N, small n, for the case of small n equals 5, show the decomposition of the sample space for all possible values of mu. Argue that for each value of mu, the collection of samples enjoys a special feature related to the simple random sampling without replacement scheme with capital N and small mu.
Okay, this is a good problem again. You know, this is all, the idea of all these questions is to make sure that you are comfortable with simple random sampling with replacement, partitioning of the total sample space, decomposition of it into different components as corresponding to the values of mu, and in this case mu will be equal to 1, 2, 3, 4, 5 because you are referring to n equal to 5. And then you have to check for yourself the nature of the samples in every pocket. Nu equal to 1, how do they look? Nu equal to 2, how do they look? And to verify that, the special feature that we are referring to is nothing but, as is stated in the text, for any value of nu, we have got n choose nu all possible samples, and each one is repeated delta nu on times. That is what you need to verify to feel for yourself that for every value of nu, it is nothing but the same repeat of basically the without replacement samples of size nu. And that's what helps you in working out, in extracting the properties of y bar star conditional on nu. Next one.
Question 4. Under simple random sampling with replacement, explain how the special feature of samples, as mentioned in question 3, is utilized in suggesting an unbiased estimator of the population mean.
Yeah. So all it says is that you try to figure out why y bar star should be regarded for every fixed nu as something related to the mean of new distinct units in a sample of size n viewed as without replacement sample, and then applying the technique of without replacement sampling, and then going back to basically use of the techniques E equal to symbolically E equal to E1 E2 and V equal to V1 E2 plus E1 V2. So at the second stage you are fixing mu, and on the first stage you are taking the expectation and variance with respect to the distribution of mu. In the second stage, the moment you fix nu, you are referring to the structure of the samples within that set, namely the samples are nothing but repeats of the core sample is without replacement sampling, and there you have the repeats. That is how you get to see the properties of y bar star tremendously simplified. What is the next question?
Under simple random sampling with replacement, capital N small n, note that two possible unbiased estimators of the population variance has been discussed. Display both of them. Critically examine the formation of the estimator based on the notion of distinct units. Argue that indeed a class of unbiased estimators can be formed based on this notion.
It is a very good question, very good question. So first you refer to with replacement sampling. You note that two possible unbiased estimators of population variance have been discussed. The first one is regard the observations as IID, and you talk about SS squared sample variance with divisor little n. It has got mean y bar and capital Y bar, and it has got variance sigma square. That is simple thing. The other thing is, think in terms of the mean based on distinct units and the variance based on distinct units, and there whenever you are talking about variance based on distinct units, you are referring to capital S square, and from there you get into sigma square. That part is okay. Now they are saying you examine the formation of the estimator based on the notion of distinct units, how it has been done, how you have ruled out the possibility of mu equal to 1. And while ruling out the possibility of mu equal to 1, you have suggested one estimator. The claim is that there is a large number of unbiased estimators that can be suggested based on what you have done, critically thinking about what you have done in giving one estimator, and that can be generalized to come up with a large number of estimators. Let's take up the MCQs quickly.
Under simple random sampling with replacement capital N small n, for the case of small n equals 5, the mode of the distribution of the number of distinct units nu is given by nu equals 2, or nu equals 3, or nu equals 4, or does depend on the value of capital N.
Okay, so in this example, we are tacitly assuming capital N to be more than 5. Okay, now you are looking at small n equal to 5, therefore the distinct units will be 1, 2, 3, 4, 5, and the problem is what is the mode of the distribution? Is it at 2 or at 3 or at 4, or it depends on the value of capital N? Interesting question, okay. What is the next one?
Under simple random sampling with replacement capital N small n, for small n equals 4, there are 8 possible unbiased estimators of the population variance based on the sample observations. Is it true, false, or depends on the value of n, which is more than 4?
Interesting question again. They are talking about unbiased estimators of the population variance. So this question is related to the exercise that was there. There is a possibility of getting beyond 2. So the question is, there are 8 possible unbiased estimators. Is it true or false or something? It depends on the value of capital N. Think about it, okay? It's a good question. What is the next one?
Under simple random sampling with replacement capital N small n, it is known that the mean based on all the units, including the repeats, has a larger variance compared to the mean based on the distinct units only. By critically examining the proof of this result, one can assert that this is just an exercise toward comparison of the mean of a positive valued random variable with a fixed given quantity, both being functions of small n and capital N. Is the assertion true, or is it false, since it depends also on the population variance?
A good question. So you look to the two expressions for the variance and look to how the comparison is being made, and whether essentially it depends on a comparison between the expectation of a positive valued random variable and a fixed quantity, or does it depend on the fact, the nature of variation in the population as well? Good question. Is that all? Okay. I think that's where we stop. Okay, thanks for your continued interest in this. We will go ahead with the next module.